August 30, 1945, Lamlash Bay, Isle of Arran, Scotland. Fleet Air Arm Lieutenant Commander David Morrison circles his Fairey Swordfish at 800 feet, staring down at what appears to be a massive hexagonal quilt floating on the choppy Scottish waters below. The runway, if you could call it that, rises and falls with the swells, each section tilting independently like scales on a serpent's back. The briefing had been clear: land a 9,000-pound torpedo bomber on a platform made of tin cans. This violates every principle of naval aviation I've ever learned. The Swordfish's fabric-covered wings shudder in the North Atlantic wind. Morrison can see Royal Navy officers standing on the undulating surface, their bodies swaying as the structure beneath them flexes with each wave. The runway measures 520 feet long and 60 feet wide, barely adequate for his aircraft's landing run. Traditional carriers are rigid steel fortresses. This thing moves like a living creature. He lines up for approach. The arrestor wires are visible, but they're mounted on a surface that won't stop moving. As Morrison descends, a motor launch passes nearby, creating a wake that sends visible ripples through the entire structure. The hexagonal units tilt and adjust, absorbing the wave energy independently while somehow maintaining a continuous surface. The wheels touch down. The Swordfish bounces once, hard, then the arrestor hook catches. The platform beneath Morrison's aircraft flexes downward under the sudden weight, then springs back. He's stopped in less than 200 feet. Morrison climbs out onto the deck that continues to undulate beneath his boots. Nearby, two civilians in suits stand examining the joints between hexagonal units. One of them, R.M. Hamilton, approaches with a satisfied expression. The platform had just supported nearly 5 tons of aircraft weight, while simultaneously conforming to wave patterns that would have destroyed a rigid structure. What Morrison doesn't know, what almost no one outside this Scottish bay knows, is that he's just validated a technology that challenges 2,000 years of engineering assumptions about what makes a stable platform. The secret isn't in fighting the ocean, it's in becoming part of it. The journey toward this bizarre floating runway had begun 3 years earlier in a very different context. By 1942, the combined operations staff under Vice Admiral Lord Louis Mountbatten faced an impossible problem: how to invade Fortress Europe without capturing a port. The Dieppe raid of August 19, 1942 had demonstrated with brutal clarity that the Allies could not expect to seize intact harbors along Hitler's Atlantic Wall. At 0500 hours that morning, 6,000 troops, primarily from the 2nd Canadian Infantry Division, assaulted the French port. The raid was a catastrophe. German defenders occupied cliff-top positions with clear fields of fire across the beaches. By 10:50 hours, the evacuation order came. Of the 6,086 men who landed, 3,623 became casualties, killed, wounded, or captured. The raid's tactical failure taught a strategic lesson. German defenses at major ports were too formidable. There would be no captured ports for Operation Overlord. Yet the invasion would require landing 150,000 men on D-Day alone, followed by thousands of tons of supplies daily. Ships needed piers, trucks needed roadways. The logistical mathematics were unforgiving. Without harbor facilities, the invasion would stall. Ronald Hamilton, working at the Department of Miscellaneous Weapons Development, proposed an answer that seemed absurd: build a floating pier that could be rolled up like a carpet and transported across the English Channel. The Swiss roll, as Hamilton called it, consisted of waterproofed canvas, stiffened with wooden slats and tensioned by steel cables. The concept was elegant: a flexible roadway that would unroll onto beaches, allowing vehicles to drive from ships to shore without bogging down in sand. Unlike traditional piers requiring months of construction, the Swiss roll could be fabricated in sections, transported by ship, and deployed by combat engineers in hours. In early 1943, 3 competing designs for Mulberry Harbour components were tested in Wigtown Bay along Scotland's Solway Firth, chosen because its 24-foot tidal range matched Normandy's coastline. Hamilton's Swiss roll competed against Hugh Joris Hughes's Hippo piers with rigid crocodile bridge spans, and a design by Lieutenant Colonel William T. Everall and Major Allen Beckett featuring floating roadways mounted on pontoons. Each system represented a different engineering philosophy. Hughes's design relied on mass and rigidity. The Everall-Beckett design used buoyancy and articulation. Hamilton's Swiss roll was pure flexibility. The trials began in calm weather. All three systems performed adequately. Then, on March 12, 1943, a North Atlantic storm swept into Wigtown Bay. Wind speeds reached 55 miles per hour. Wave heights exceeded 15 feet. Hughes's Hippo piers settled into the soft sand at different rates under the pounding waves. The rigid crocodile bridge spans couldn't accommodate the differential settlement. Steel girders buckled and twisted. By the storm's second day, 3 crocodile spans had failed completely. Hamilton's Swiss roll survived the waves but revealed a fatal flaw. The 7-ton load limit meant it could handle personnel, but nothing heavier. A Sherman tank weighing 30 tons would tear through the canvas. The flexible roadway that worked beautifully for foot soldiers was useless for the mechanized invasion the Allies needed. The Everall-Beckett design, later codenamed Whale, survived the storm intact. Its floating pontoons, called beetles, could rise and fall with the tide, while telescoping spans adjusted to changing water levels. The Whale system was selected for the Mulberry harbors, but Hamilton had learned something crucial. The failure of rigid structures in dynamic ocean conditions revealed a fundamental principle. Flexibility, not rigidity, created stability in rough seas. The Swiss roll's weakness wasn't its flexibility, that was its strength. The weakness was the canvas material. Some Swiss roll sections were used at Normandy on June 6, 1944, allowing troops to wade from landing craft with dry boots, but Hamilton had already moved on to a more ambitious application. Watching the Whale pontoons rise and fall with channel tides during the Normandy landings, Hamilton recognized the power of articulated platforms. The Whale could support 40-ton tanks precisely because it didn't fight the ocean's movement. Each pontoon adjusted independently, distributing loads hydrostatically. What if, instead of a roadway for trucks, you could create a floating platform for aircraft? Not just a pier for static loads, but a genuine runway capable of absorbing landing impact forces. The idea seemed impossible. Aircraft carriers required rigid flight decks, 24,000 tons of steel providing an immovable platform. How could a floating platform, subject to wave action, possibly remain stable for flight operations? Hamilton believed the answer lay in articulation, not a single platform fighting the waves, but hundreds of small units flexing independently while maintaining surface continuity. He began designing his floating airfield in late 1944. By late 1944, as Allied forces advanced across the Pacific, a new strategic challenge emerged. The invasion of Japan, codenamed Operation Downfall, would require unprecedented air support. Aircraft carriers were vital, but limited in number and vulnerable to kamikaze attacks. Shore bases wouldn't exist until after the most brutal phase of fighting. The strategic mathematics were unforgiving. Operation Olympic, the invasion of Kyushu scheduled for November 1, 1945, would involve 815,548 men. Operation Coronet, the assault on Honshu planned for March 1946, would commit an additional 1,171,646 troops. The invasions would dwarf Normandy by a factor of 5. Air support for these operations required impossible numbers. The Joint Chiefs estimated 3,000 aircraft would need to operate continuously over the invasion beaches, fighters providing air superiority, dive bombers striking coastal defenses, torpedo bombers interdicting Japanese naval forces. The Royal Navy examined the carrier mathematics. Each illustrious class fleet carrier could operate approximately 50 aircraft. Building new carriers required 24 to 36 months. The invasion timeline didn't permit that luxury. Moreover, the kamikaze threat made every carrier precious. Between October 1944 and August 1945, kamikaze attacks had damaged or sunk 82 American vessels. The British Pacific Fleet faced additional constraints. Operating 6,000 miles from the nearest major base, Royal Navy carriers couldn't rely on shore facilities for maintenance or crew rest. Every sortie consumed fuel transported from British refineries. Every lost aircraft had to be replaced from production lines already supporting European operations. Hamilton saw an opportunity. His Swiss roll had demonstrated that flexible structures could survive conditions that destroyed rigid platforms. What if that principle could create floating airfields that could be towed to forward positions, requiring no capture of enemy territory, no vulnerability of valuable carriers? The concept was radical. A deployable runway assembled at sea, towed into position off enemy coasts, and operated as a forward airbase. Aircraft could land, refuel, rearm, and launch without returning to distant carriers. The platform would be expendable. If destroyed, another could be assembled. No crew of 2,000 would be lost. Working with J.S. Herbert, a mathematics housemaster at Eton College, Hamilton refined his concept. Herbert's background in geometry and structural mechanics proved essential for calculating the forces at work when a flexible platform supported concentrated loads. The design that emerged was radically different from Swiss roll. Instead of canvas, Hamilton proposed hexagonal steel cans, each 6 feet across and 30 inches deep, topped with steel plates. The revolutionary element was the hinge system connecting the units. Each hexagon could tilt independently in response to wave action, yet when linked together, the hexagons created their own hydrostatic tension. The principle was counterintuitive. Traditional naval engineering assumed stability required rigidity. Hamilton and Herbert proposed the opposite, a structure so flexible it never fought the ocean's energy, but instead absorbed and distributed it across hundreds of independent units. Herbert's calculations revealed the mathematics. A traditional rigid platform experiences maximum stress when a wave crest reaches its center, essentially trying to snap the structure in half. Hamilton's articulated design distributed wave energy across multiple joints, with each hexagon tilting just enough to follow the wave surface. Herbert calculated that a 520-foot platform composed of these hexagonal units would remain stable for aircraft operations in seas up to 35 feet, wave heights that would force fleet carriers to suspend flight operations. The Admiralty approved construction of a prototype in late 1944. The project received modest funding, £50,000, a fraction of an escort carrier's cost. Testing would occur at Lamlash Bay on the Isle of Arran, sheltered enough for safe trials but exposed enough to generate realistic sea conditions. By early 1945, as fabrication began, the Pacific War had reached critical intensity. American forces captured Iwo Jima between February 19 and March 26, suffering 26,038 casualties to seize 8 square miles. Okinawa, invaded April 1st, proved even bloodier, 82,000 American casualties, including 12,500 killed by June 22nd. Japanese casualties exceeded 100,000 soldiers, plus an estimated 150,000 Okinawan civilians. Casualty projections for invading the Japanese home islands ranged from 500,000 to over 1 million Allied soldiers. Every innovation that might reduce those numbers demanded urgent attention. The floating airfield, codenamed Lily, represented a radical gamble. If it worked, the Allies could establish forward air bases without carriers or captured territory. Hamilton needed to prove physics would cooperate with his vision. March 1945, Lamlash Bay. The first hexagonal units arrived by truck from fabrication sites around Scotland. Each steel can weighs approximately 200 pounds empty, light enough for 4 men to maneuver into position, heavy enough to provide substantial buoyancy when sealed and deployed. The fabrication process has been deliberately simplified for rapid production. Each hexagon is constructed from 16-gauge steel plate welded into a cylindrical drum with a hexagonal cross-section. Watertight seals ensure the units remain buoyant even if damaged. The design allows any metal shop with basic welding equipment to produce units. The assembly process reveals the elegance of Hamilton's design. Unlike the massive phoenix caissons of the Mulberry harbors, which required floating docks and specialized equipment, Lily's components can be assembled by a small crew using hand tools. The hexagons are lowered into the water and linked via pin and hinge connections that allow controlled articulation. Royal engineers supervise as civilian workers connect the units in a honeycomb pattern. The hinge design is crucial. It must allow 15 degrees of tilt while remaining strong enough to transfer loads. Each hinge consists of a steel pin passing through reinforced lugs. The pins are retained by split pins, allowing rapid assembly. Steel plates are bolted to the top of each hexagon, creating a continuous metal surface. Each plate measures 6 feet across, with flanges that overlap adjacent plates by 6 inches. This overlap maintains surface continuity while allowing the underlying hexagons to tilt independently. Initial tests with partial assemblies are promising. A 50-foot section floats stably and conforms to wave patterns exactly as Herbert's calculations predicted. Men can walk across the surface with only minimal sensation of movement. The structure flexes beneath their feet, but the motion is gentle and controlled. The workers discover that the platform exhibits unexpected properties. When someone walks across it, their weight creates a local depression. The hexagons beneath their feet compress slightly, while neighboring units tilt to accommodate the load. The effect demonstrates that the platform truly distributes loads hydrostatically. By April 1945, the assembly has grown to 200 feet. Maintaining alignment requires careful attention. If hexagons are connected even slightly out of position, accumulated error can create gaps or binding. The Royal Engineers develop a technique, assemble in 50-foot sections, verify alignment, then connect sections together. By May 1945, the full 520-foot by 60-foot platform is complete. Assembly has taken approximately 400 man-hours, dramatically less than weeks required for traditional pier construction. The total weight is approximately 5,000 tons, yet the structure floats with remarkable stability. Hamilton and Herbert stand at one end, watching as a motor launch passes at full speed. The wave pattern hits the platform broadside. Individual hexagons tilt rhythmically, but the steel deck surface remains continuous. The wake energy dissipates across hundreds of articulated joints. Within seconds, the platform returns to neutral position. The next test is crucial, loading with concentrated weight. A 7-ton truck is driven onto the surface. The hexagons beneath the wheels compress slightly, sinking perhaps 3 inches, but neighboring units compensate, tilting to maintain surface continuity. The truck parks in the center, traditionally the point of maximum stress. Lily simply adjusts, surrounding hexagons tilting fractionally to maintain equilibrium. But a truck is not an aircraft. The Fairey Swordfish Mark III weighs 9,000 pounds fully loaded, and that weight will be traveling at 80 miles per hour when it touches down. The impact forces will be substantially greater. Moreover, the aircraft will need to stop in the limited 520-foot runway length, requiring arrestor wires and hydraulic braking systems. Fleet Air Arm engineers arrive in June 1945 to install the arrestor gear. The system is adapted from carrier technology. Steel cables stretched across the runway at 3-foot height, connected to hydraulic dampers that can absorb the kinetic energy of a landing aircraft. The difference is that traditional carrier arrestor gear is mounted to a rigid steel deck anchored to 20,000 tons of ship. Lily's arrestor wires are mounted to a flexible platform that weighs 1/4 as much and floats freely. Herbert's mathematics suggest the hydrostatic resistance of 5,000 tons combined with distributed load across hundreds of hexagons should provide sufficient inertia to stop a swordfish. The arrestor dampers are calibrated for lighter platform mass, allowing them to absorb more energy mechanically. 3 arrestor wires are installed at 50-foot intervals. The wires are tensioned to 800 pounds each, tight enough to catch the arrestor hook reliably but loose enough to allow platform flex without breaking the cables. There's only one way to find out if the theory matches reality. Naval engineering has always been about fighting the ocean. Battleship hulls are designed to resist wave impact. Carrier decks are rigid platforms that barely flex under aircraft weight. Breakwaters stand immobile against storm surge. For 2 millennia, the engineering response to ocean forces has been build stronger, build heavier, build more rigid. Hamilton and Herbert proposed the opposite philosophy. Don't fight the ocean, become part of it. The requirement that led to Lily was simple but demanding. The Admiralty needed forward air bases that could be assembled without specialized equipment or facilities, support aircraft up to 9,000 pounds weight, operate in sea states that would ground traditional carriers, be transportable by ship and deployable in 24 hours, require minimal maintenance. Traditional engineering could meet none of these requirements. A rigid platform strong enough to support 9,000-pound aircraft would require massive structural members and deep foundations, impossible to transport and deploy quickly. A platform light enough to tow would flex and fail under aircraft weight. Hamilton's solution was to reject the fundamental assumption. Instead of preventing flexure, he designed a structure that flexed in a controlled, predictable manner. Each hexagonal unit could tilt up to 15 degrees relative to its neighbors, far more movement than any traditional bridge or pier would permit. Yet when linked together, the hexagons created a surface that was stable precisely because it was flexible. The physics involved hydrostatic tension, the same principle that allows a waterbed to support weight evenly. When an aircraft landed on Lily, the hexagons directly beneath the wheels compressed downward, increasing their displacement and buoyancy. This created a local basin in the platform. Surrounding hexagons tilted inward slightly, maintaining continuity across the surface while distributing the load across dozens of units. As waves passed beneath the platform, each hexagon followed the wave surface independently. The steel deck plates maintained continuous coverage, but underneath, the structure was in constant gentle motion. An aircraft parked on Lily would experience slight rolling motion, about 5 degrees, but the surface remained level enough for safe operations. Herbert's calculations revealed that this flexibility actually improved stability in rough seas. A rigid platform fights wave energy, creating stress concentrations at fixed points. Lily absorbed wave energy across hundreds of articulated joints. In 35-foot seas, wave heights that would force fleet carriers to suspend flight operations, Lily would simply undulate gracefully, never accumulating sufficient stress to fail. The trade-offs were carefully calculated. Hamilton sacrificed the solid confidence of rigid construction for the adaptive resilience of articulated design. Each hinge represented a potential failure point, yet the distributed nature of the system meant that even if several hinges failed, neighboring units would compensate. The decision to use hexagonal units rather than squares or rectangles was deliberate. Hexagonals tessellate efficiently, leaving no gaps, while allowing 3 degrees of rotational freedom at each joint. A square grid would bind at the corners. Hexagons could tilt in any direction while maintaining surface contact. The choice of 6-foot hexagons represented the minimum size that could provide adequate buoyancy while remaining transportable by standard trucks. Larger units would have simplified assembly but complicated logistics. Smaller units would have increased fabrication costs without improving performance. This engineering philosophy, yielding rather than resisting, distributing rather than concentrating, adapting rather than standing firm, represented a profound shift in thinking about how structures interact with dynamic environments. The question was whether reality would validate the theory. July 15, 1945, the Fairey Swordfish Mark III sits at the far end of Lily's runway, its Bristol Pegasus 30 radial engine idling. Rocket-assisted takeoff gear is mounted under the starboard wing, 2 solid-fuel rockets designed to reduce takeoff run from 650 feet to 270 feet. Lieutenant Commander Morrison performs his pre-flight checks while Hamilton and Herbert observe from the platform's edge. The Swordfish is an anachronism by 1945 1945 standards, a fabric-covered biplane in an era of sleek monoplane fighters. First flown in 1934, the string bag has survived in Fleet Air Arm service primarily for anti-submarine work and training duties. Its maximum speed of 138 miles per hour makes it hopelessly obsolete as a combat aircraft, but its slow landing speed of 65 miles per hour and docile handling characteristics make it ideal for experimental carrier trials. Morrison's aircraft weighs 8,700 pounds with a partial fuel load and no ordnance, close enough to the 9,000-pound design limit to stress test the platform. The test sequence is carefully structured. First, a takeoff using RATO to verify the platform can handle asymmetric thrust loads and acceleration forces. Then, a landing without arrestor wires, allowing Morrison to judge the surface's stability. Finally, a full arrested landing simulating carrier operations. Morrison advances the throttle. The Pegasus engine roars to full power, 690 horsepower at 2,250 RPM. The Swordfish's tail wheel lifts as the biplane begins its takeoff roll. The platform beneath the aircraft compresses slightly, the hexagons tilting to distribute weight. At 60 miles per hour, Morrison fires the RATO rockets. White exhaust plumes shoot backward as the solid fuel burns, adding 1,000 pounds of thrust. The Swordfish accelerates rapidly, pressing Morrison back in his seat. The platform responds to the sudden acceleration. Hexagons at the rear compress more deeply than those at the front as the aircraft's weight transfers aftward. The asymmetric loading creates a slight bow wave in the platform's surface, but the structure absorbs the forces without failing. The critical moment comes as the aircraft rotates for takeoff. The concentrated weight on the main landing gear, combined with the upward rotation force, creates a complex loading condition. The hexagons beneath the wheels compress, tilt, and spring back as the aircraft lifts off. The platform flexes through perhaps 6 inches of total movement, then rebounds to level. Morrison is airborne in less than 300 feet, climbing away over the bay. He circles at 1,000 feet, giving the platform time to settle. From altitude, Lily looks surreal, a geometric pattern floating on dark water, clearly artificial yet somehow organic in its movement. Morrison can see waves approaching from the open ocean, each swell causing the platform to undulate in a slow, sinuous motion. The surface appears to breathe, rising and falling gently with each wave passage. For the first landing attempt, Morrison comes in without using arrestor wires. He needs to feel how the platform responds to his aircraft's weight during the rollout. The approach is standard carrier procedure. Maintain 65 miles per hour, aim for the first 100 feet of deck, be ready to add power and abort if the landing looks wrong. The Swordfish descends through 200 feet, 100 feet, 50 feet. Morrison can see Hamilton and Herbert standing clear of the runway, watching intently. At 20 feet, Morrison reduces power slightly, flaring the biplane for touchdown. The wheels contact the steel plates with a metallic thump. Morrison feels the platform compress beneath him, a sensation unlike any carrier landing. There's a yielding quality, a slight bounce as the hexagons adjust to the impact. The sensation is disconcerting but not dangerous. The platform has given way perhaps 4 inches, creating a shallow depression under the aircraft's weight. He lets the Swordfish roll, using minimal braking. The platform's surface is stable enough, but there's perceptible motion as the aircraft passes over different hexagons, a gentle rippling sensation transmitted through the landing gear. Morrison brings the Swordfish to a stop 400 feet from touchdown, twice the distance he'd need on a traditional carrier deck, but acceptable given the experimental nature of the platform. He taxis back to the starting position, the Swordfish's weight creating a moving depression in the platform's surface. The hexagons compress under the aircraft, then spring back up after it passes. The effect is like driving across a waterbed. Engineers swarm over the platform, examining hinge connections for signs of stress. The joints show minimal wear, exactly as predicted. The distributed load design means no single hinge has experienced excessive force. The platform has handled takeoff and landing forces without structural damage. The next test is the critical one, a full carrier landing with arrestor wires. Morrison climbs to 1,000 feet and sets up for the approach. This time he'll come in at normal carrier landing speed and let the arrestor hook catch the wires. Either the platform will absorb the shock loads or it will fail catastrophically. He commits to the approach. The Swordfish descends through 500 feet, 300 feet, 100 feet. Morrison holds his speed steady at 75 miles per hour, faster than his previous landing, generating more impact force. He aims for the second arrestor wire, the recommended target on carrier approaches. The wheels slam down, harder this time, a deliberate heavy landing to stress test the system. The arrestor hook drops, skips once across the deck plates, then catches the second wire with a metallic shriek. The deceleration is violent. Morrison is thrown forward against his harness as the Swordfish goes from 75 miles per hour to 0 in less than 200 feet. The arrestor wire stretches, the hydraulic dampers scream, and the entire structure compresses downward under the sudden load. For a moment, Morrison thinks the structure will be pulled apart. The hexagons beneath the arrestor wire attachment points compress dramatically, perhaps 12 inches, while the aircraft's kinetic energy transfers into the arrestor dampers. Then, it's over. The Swordfish sits motionless, still attached to the arrestor wire. The arrestor dampers have absorbed the majority of the kinetic energy, approximately 1.2 million foot-pounds, while platform inertia and hydrodynamic resistance provided the reaction force. Hamilton and Herbert are running toward the aircraft, faces split by grins. As Morrison cuts the engine, the platform slowly rebounds to neutral position. The entire arrest sequence has lasted 3.2 seconds. The arrested landing has subjected Lily to forces equivalent to a 15-ton vehicle hitting the deck at high speed and stopping in the length of a tennis court. The structure absorbed shock loads that would have buckled many traditional piers. The secret was in the distributed response. No single hexagon or hinge bore the entire force. Instead, the energy spread across the entire platform like ripples on a pond. Over the following weeks, Morrison conducts repeated takeoffs and landings. The platform proves capable of handling multiple aircraft operations per day with minimal maintenance. The hexagonal units require occasional inspection for hinge wear, but the simplicity of the design means repairs can be performed with basic tools. A single bent hinge pin can be replaced in less than 30 minutes using a hammer and drift punch. The trials reveal interesting operational characteristics. Aircraft taxiing on Lily must maintain steady speed. Sudden acceleration or braking creates localized platform depressions that can affect control. Pilots learn to taxi smoothly, allowing the platform to respond gradually to weight changes. Parking aircraft on the platform requires careful placement. Concentrating multiple aircraft in one area creates a deep depression that can complicate takeoffs. One test stands out. On August 12, 1945, Morrison conducts operations during a force 6 gale, wind speeds of 39 to 46 miles per hour with wave heights reaching 20 feet. Fleet carriers typically suspend flight operations in such conditions, the pitching and rolling making carrier landings dangerous. The illustrious-class carriers can roll up to 15 degrees in heavy seas, creating impossible landing conditions. Lily continues to function. The platform rises and falls with the swells, undulating dramatically as 20-foot waves pass beneath. Individual hexagons tilt through their full 15-degree range of motion, the surface appearing to writhe like a living thing. Yet the steel plates maintain continuous coverage, and the arrestor wires stay in position. Morrison's approach is challenging. The platform is rising and falling through a vertical range of 15 feet, forcing him to time his landing to catch the platform near the top of its rise. He comes in fast, 80 miles per hour to maintain control in the gusty winds. The touchdown is rough, the Swordfish bouncing twice before the arrestor hook catches. The platform flexes violently under the impact, but the arrest completes normally. The trials demonstrate that Hamilton's flexibility principle works as predicted. A platform that yields to ocean forces can remain operational in conditions that would ground rigid structures. The articulated design prevents stress concentrations, distributing forces across hundreds of joints. The result is a runway that moves with the ocean rather than fighting it, and paradoxically remains more stable precisely because it's flexible. Lily Floating Airstrip. Specifications and performance. Physical dimensions. Length 520 feet, 158.5 meters. Width 60 feet, 18.3 meters. Total surface area 31,200 square feet. Individual hexagon diameter 6 feet, 1.83 meters. Hexagon depth 30 inches, 76.2 centimeters. Number of hexagonal units approximately 280. Weight and capacity. Total platform weight 5,000 tons. Maximum aircraft weight tested 9,000 pounds. Fairey Swordfish Mark III. Designed capacity up to 9,000 pounds concentrated load. Distributed weight limit substantially higher, untested. Assembly and construction. Man-hours required for assembly 400 hours. Crew size for assembly 40 men. Assembly time experienced crew approximately 10 hours. Disassembly time comparable to assembly. Operational capabilities. Maximum safe wave height 35 feet. Design specification. Tested wave heights 20 feet. Force 6 gale conditions. Platform flex range plus or minus 5 degrees from horizontal. Individual hexagon tilt range plus or minus 15 degrees relative to neighbors. Arrestor wire deceleration distance 150 to 200 feet. Testing results 1945. Total flight operations conducted approximately 50 takeoffs and landings. Aircraft types tested Fairey Swordfish Mark III. Radar-assisted takeoffs reduced distance from 650 feet to 270 feet. Test period duration March to August 1945. Platform failures during testing 0 structural failures. Maintenance requirements, minimal hinge inspection and lubrication. Comparative analysis. Fleet carrier flight deck length 700 to 800 feet typical. Escort carrier flight deck length 450 to 500 feet. Lily runway length 520 feet. Fleet carrier displacement 20,000 to 30,000 tons. Lily platform weight 5,000 tons, or 16 to 25% of carrier displacement. Projected operational deployment. Intended theater, Pacific Ocean. Operation Downfall. Planned deployment, forward air bases supporting invasion of Japan. Actual combat use, none. War ended before deployment. Post-war testing continued through late 1945. August 30th, 1945. The last Swordfish lands on Lily as Royal Navy photographers document the final trials. 6 days earlier, Japan had formally surrendered aboard USS Missouri in Tokyo Bay. Operation Downfall has been canceled. The floating airstrip that might have supported the invasion will never see combat. Hamilton walks the length of the platform one final time, examining the hexagonal joints that have performed flawlessly through months of testing. The concept worked, perhaps too well for its own good. Had the war continued into 1946, fleets of Lily platforms might have dotted the waters off Kyushu, providing forward air bases without the vulnerability of carriers or the need to capture enemy airfields. The platforms could have been assembled in British ports, towed across the Pacific by tugboats, and positioned wherever air support was needed. The operational advantages were considerable. A traditional fleet carrier required a crew of 2,000 and represented years of industrial effort. Lily required a maintenance crew of perhaps 50 and could be assembled in days from components produced by any fabrication shop. If damaged by enemy action, a carrier represented catastrophic loss of men and materiel. Lily was expendable. Hexagonal sections could be replaced individually, and if necessary, an entire platform could be abandoned without loss of trained crew. The cost differential was equally striking. The Admiralty's £50,000 investment in Lily's prototype represented less than 1% of a fleet carrier's cost. Mass production of hexagonal units could have created dozens of floating platforms for the price of a single carrier. The strategic implications were profound. Instead of concentrating air power on vulnerable ships, the Allies could have dispersed aircraft across multiple expendable platforms. Instead, Lily becomes a footnote, a successful proof of concept for a capability the Allies no longer need. The platform is disassembled over the following months, the hexagonal units dispersed or scrapped. A few photographs and technical reports preserve the project's details for naval historians. Hamilton's name appears in occasional engineering journals discussing innovative marine structures, but Lily itself fades from memory. But the principle Hamilton and Herbert validated, that flexibility creates stability, that yielding generates strength, does not disappear. In the decades after the war, engineers designing offshore oil platforms, floating bridges, and marine structures repeatedly rediscover the insights embedded in Lily's articulated hexagons. The North Sea oil boom of the 1970s produces floating platforms that use articulated joints to handle 50-foot waves, exactly the principle Hamilton demonstrated in 1945. Modern floating airports in Japan employ segmented runways that flex with wave action rather than resisting it. Floating construction platforms worldwide use variations of Hamilton's concept, articulated segments that distribute loads and absorb wave energy. The mathematics Herbert calculated in 1945, how concentrated loads distribute hydrostatically across flexible platforms, how articulated joints prevent stress concentrations, how yielding structures can be more stable than rigid ones, inform contemporary finite element analyses of flexible marine structures. Engineering students learning about dynamic response to wave loading unknowingly study principles first proven on a Scottish bay with hexagonal steel cans. The Mulberry harbors at Normandy, where Hamilton's Swiss roll played a minor role, are remembered as one of the war's great engineering achievements. Lily, which proved a more sophisticated application of the same flexibility principle, is largely forgotten. Perhaps because Mulberry saw combat while Lily did not. Perhaps because temporary floating piers are more intuitively comprehensible than undulating aircraft runways. Perhaps because history prefers victories to might-have-beens. Or perhaps because Lily's most important contribution wasn't military but conceptual, a demonstration that engineering orthodoxy about rigidity and strength could be wrong, that sometimes the right answer to how do we build something that won't break is design it to bend, that the strongest structure isn't always the one that refuses to move. The hexagonal units that made up Lily were simple enough, steel drums with hinges, topped with plates. The revolution was in recognizing that hundreds of such units, properly connected, could create a surface more stable than any rigid structure. That the ocean's energy, properly distributed, becomes a source of stability rather than a threat. That fighting nature is often less effective than working with it. In 1945, standing on a platform that rose and fell with Scottish swells while supporting multi-ton aircraft, Hamilton proved that naval engineering's oldest assumption, that platforms must be rigid to be strong, was false. The platform that flexed was the platform that endured. The runway that moved with the waves was the runway that remained operational when rigid structures failed. That principle, validated in a sheltered Scottish bay during the final months of a global war, continues to shape how we build structures that must survive in dynamic environments. Lily never fired a shot, never supported a combat mission, never saw the Pacific waters it was designed to conquer. The war ended before the concept could be proven in battle, but it demonstrated a truth more durable than steel, more valuable than tactical victory. The strongest structure isn't the one that refuses to yield, it's the one that knows how to bend without breaking. In an age that worshipped mass and rigidity, Hamilton and Herbert proved that sometimes the best engineering solution is the one that seems impossible until someone builds it.